Microservices Patterns, the complete architecture guide. Building scalable, resilient systems with proven patterns. Introduction: the microservices revolution. In the world of modern software architecture, microservices have transformed how we build and deploy applications. Rather than creating monolithic systems that become increasingly difficult to maintain and scale, microservices offer a modular approach where applications are built as a collection of loosely coupled, independently deployable services. This comprehensive guide explores the essential patterns that make microservices architecture successful, organized into 9 critical categories that every architect and developer must master. 1. Decomposition, breaking down the monolith. The foundation of microservices lies in how we decompose our applications into manageable, focused services. Domain-driven design, DDD, the cornerstone of effective microservices decomposition. DDD helps identify natural boundaries within your business domain, ensuring each service owns a specific business capability. Instead of technical boundaries, you create services around business concepts like user management, order processing, or inventory control. Bounded context. Each microservice should operate within a clearly defined bounded context, a boundary within which a particular domain model is valid. This prevents the common pitfall of shared databases and ensures each service can evolve independently. Backend for frontend, or BFF. Recognizing that different client types, mobile apps, web applications, APIs, have different needs, BFF creates specialized backend services tailored to specific front-end requirements, reducing overfetching and improving performance. 2. Configuration, managing service settings. In a distributed system, configuration management becomes crucial for maintaining consistency and enabling flexibility. External configuration. Store configuration outside your code in environment variables, configuration servers, or cloud-based configuration services. This enables the same service to run in different environments without code changes. Centralized configuration. Use tools like Spring Cloud Config, Console, or etcd to manage configuration across all services from a single source of truth. This ensures consistency and enables dynamic configuration updates. Distributed configuration. Balance centralization with service autonomy by allowing services to maintain their own configuration while inheriting common settings from centralized sources. 3. Resiliency. Building fault-tolerant systems. Microservices architectures are inherently more complex, making resilience patterns essential for maintaining system stability. Retry pattern. Implement intelligent retry mechanisms with exponential backoff and jitter to handle transient failures. Not all failures are permanent. Many network issues, temporary resource constraints, or brief service unavailability can be resolved with well-designed retry logic. Circuit breaker. Prevent cascading failures by implementing circuit breakers that trip when a service becomes unhealthy, allowing the system to fail fast and recover gracefully. Popular implementations include Historix, Resilience 4J, and cloud-native solutions. Bulkhead pattern. Isolate critical resources to prevent failure in one area from affecting others. Just as ship bulkheads prevent water from flooding the entire vessel, software bulkheads isolate thread pools, connection pools, and other resources. Timeout management. Set appropriate timeouts for all inter-service communications to prevent cascading delays and resource exhaustion. Fallback mechanisms. Define graceful degradation strategies when services are unavailable, such as returning cached data, default values, or simplified responses. Rate limiting. Protect services from overload by implementing rate limiting at various levels, per user, per service, or globally. 4. Integration. Connecting services effectively. How services communicate determines the success or failure of your microservices architecture. API gateway. Create a single entry point for all client requests, handling cross-cutting concerns like authentication, rate limiting, request routing, and response aggregation. Popular solutions include Kong, AWS API Gateway, and Zool. API facade. Simplify complex service interactions by providing simplified interfaces that aggregate multiple service calls into single operations. Service mesh. Implement infrastructure-level service communication with tools like Istio, Linkd, or Console Connect, handling service discovery, load balancing, security, and observability automatically. Choreography versus orchestration. Choose between event-driven choreography, services react to events, or centralized orchestration. A coordinator manages the workflow, based on your use case complexity and team preferences. Service registration and discovery. Enable services to find and communicate with each other dynamically using service registries like Eureka, Console, or cloud-native solutions. 5. Versioning. Managing evolution. In a microservices world, services evolve independently, making versioning strategies critical. Semantic versioning. Use semantic versioning, major.minor.patch, to communicate the impact of changes clearly. Breaking changes increment the major version, new features increment minor versions, and bug fixes increment patch versions. API versioning. Implement API versioning strategies such as URL versioning, /v1/users, header versioning, or content negotiation to maintain backward compatibility while enabling evolution. Database. Data management patterns. Data management in microservices requires careful consideration of consistency, performance, and service boundaries. Database per service. Each microservice should own its data completely, preventing tight coupling and enabling independent scaling and technology choices. CQRS. Command Query Responsibilities Segregation. Separate read and write operations to optimize for different patterns and scale read and write workloads independently. Saga pattern. Manage distributed transactions across multiple services using the Saga pattern, which breaks long-running transactions into smaller, compensable steps. Compensatory transactions. Implement rollback mechanisms for distributed operations by defining compensatory actions that can undo previously completed steps.